there's only one more thing that I would like to do from a theoretical perspective, which is anomalous diffusion, which is what I'll do for the next whatever. So today I thought we'll do two examples again of backward equations before we move on to anomalous diffusion and anomalous transport. So what I will follow today is this paper, which I think I may have said earlier as well. First passage processes in cellular biology by Srividya Iyer Biswas and Anton Zillman. So this is a sort of review of first passage processes in cellular biology. It has a lot of the formalism as well, briefly. In fact, I think this is partially where my backward notes are from. And then it has a bunch of examples in biological context where you use these methods. Okay, so today I'll discuss one of these examples, which is cell division. So cell growth and division. Okay, so that's what we'll discuss today. Here, the name, Srividya Iyer Biswas and Anton Zillman. I think this is in 2015. You give the name, it will come first person. So there is actually one more nice paper by, it's called something similar. By Tom Chow, first passage. It's by Tom Chow, and since I have this anyway, let me just look at this first passage. There is another review paper, first passage problems in biology, Chow and Diorsonia. This is also a very nice paper. It is also a review. Again, it discusses various biological problems through this framework of the backward equations, first passage, and so on and so forth. Okay, in various contexts. So both of these are actually nice papers to read because it puts all of these things that we've been doing into some specific biological applications. And both of these are available on arXiv. Both this one and this Tom Chow are available on arXiv. So, all right. So the first problem that I want to discuss is that of cell growth and essentially cell division. So here's the thing. So here is, for example, a cell. I think this is the bacteria Caulobacter crescentus. So this is these are experimental snapshots of Caulobacter crescentus cell, I think taken at 20-minute intervals, and you can see that the size of the cell, so marked by this boundary, it is sort of increasing until it sort of will start to divide. Okay, so a cell is born, and then it keeps on growing with time. At some point, it starts to divide and produces two daughter cells. Okay, so that's the process that we are interested in. So the first, what we want to ask is that what is the time that it takes for this cell to divide into two? So what is this cell division time? And that is what we'll try to cast as a first passage problem. But before that, how does this cell grow? So when I say that the cell grows with time, how does it grow? And if you people have done these sort of experiments, and it seems that, so for example, if you were to measure the area of this cell as a function of time, this is what you see. So this is area as a function of time on the first hand. These are multiple experiments. I think these are different generations of the same cell. So you take this, you plot the area as a function of time, you get something like this. Then the cell divides. You start with some starting area. So, of course, you don't start with 0, but you start at somewhere, some small area, and then you grow, grow, grow. At some point, you again divide, and again the daughter cell starts. Okay. So, these are multiple, these are experimental traces of the area versus time of multiple cells and multiple generations. If you plot this on a semi-log scale, so this is the same data on a semi-log scale for this Caulobacter crescentus, you see that you get straight lines, which means that the area is increasing exponentially with time, right? So, on the semi-log scale, it's a straight line, which means it's increasing exponentially. And this is something that is often seen in various contexts, that if you, it seems that cell sizes often grow exponentially. So, cell sizes grow exponentially with time. Okay. That's one possibility. So, this is one experiment. There are others. So, this is another experiment, this time with E. coli. Again, and in this case, they were measuring the length of the E. coli, and this is this traces of this length versus time. Again, multiple generations of the bacteria. So, it grows and then it again shrinks when it divides and so on. And again, in this case, if you were to plot it on a semi-log scale, you'll see that it again the cell sizes grow exponentially with time. So, these are one set of experiments. There are other experiments which have shown linear growth. So, this is again actually, as it turns out, E. coli. This is a slightly older experiment. So, this is 1968. I think the previous one is, yeah, it's fairly recent. It's 2010. But doesn't matter. So, that doesn't mean that this is wrong. So, here is again cell volume of E. coli versus time, and here you roughly see something like linear growth actually instead of exponential growth, right. So, these are both axes are linear and you get a straight line. Okay. So, it depends on what sort of media you are putting your cell in. Generation times can change. Here, how much is it? It is yeah, so this is 100 minutes. I don't know how many generations is in here, but yeah, definitely much faster than the second case. So, I want us to see. So, there is a thing. So, these are different. The same cell under different conditions can take different sort of times. So, this one, if I remember correctly, is inside some microfluidic channel. These set of experiments, whereas these ones were probably in the bulk. And again, it depends on what sort of medium you have put your bacteria under. All right. So, this is the other option, that sometimes experimentally they've seen that cell sizes grow linearly with time. So, you can have either exponential growth or you can have linear growth. Okay. So, that's number one, that if you plot the size of the cell as a function of time, if you plot the size of the cell S as a function of time, you can either have something like this mostly or something like this. Okay. And then the question is that when does the cell divide? Okay. It grows like this, either linearly or exponentially, and then at some point it divides. So, there are three possibilities that we'll discuss. And this has to do with how you think of this thresholding. So, for example, you could say two things. So, three things, that I have the size as a function of time, and you say that, well, I should not draw like this because it does not start from 0, because when a daughter cell is born, it's born with some size, right, not 0 size. So, let us say it's born with something like this. Right. So, this is some S naught that your daughter cell starts off with, and you could say there is some absolute threshold, that when the cell crosses, for example, some absolute size theta, let us say, this is when it will divide. And then the question is that through this process where you have exponential growth or linear growth, what is the distribution of times that you hit this size theta, right. So, that would be an example of absolute thresholding, that if your cell gets to some size theta, you divide. So, over here you will divide, and then you look at the distribution of times. You could have something like differential thresholding, which says that, well, I have started with S naught and maybe I need to grow to S naught plus some theta, and that is when I will divide. So, this thing, if when it is S naught plus theta, then is when it will divide. If I have a different cell which starts off with a different initial area, different initial size, let us say I have another cell which starts off like this, right. So, this is the S naught prime for this cell, the theta stays the same. So, S naught prime plus theta. So, this is S naught prime plus theta. So, this cell will divide when it hits this value, okay, and this first cell will divide when it hits this value. So, there is no absolute size threshold, but there is some differential threshold where you have to add a certain amount of area before you get to this cell division. Okay. So, that is called this differential size threshold. The third is what is called as this ratio size threshold, where again you say that I start with some S naught. Theta is not fixed. So, in that sense, or rather theta is not something that you know as such, but so this is under the assumption that the cell knows that there is some critical size that it has to reach. Once it reaches that size, it divides. So, that is a hypothesized mechanism, that how do I sort of go about modeling cell division in terms of these cell sizes. I say there is some parameter theta which is the desired critical size, and then once the cell reaches that size, you divide. Of course, then therefore, the answer that you will get, that what is the distribution of cell division times, will be parameterized by what theta you choose, and then in principle you could go back to the experimental curves, see that whether the form of the distribution matches, and if it matches, for what value of theta it matches. In this second sort of thing that I was saying, in this differential size thresholding. So, again, these are all hypotheses. There is none of these is a proved mechanism. So, this is just how we are starting to think about, or how people started to think about cell division. So, one is they say that yes, there is an absolute theta. It does not matter where you. So, this is my size as a function of time. Some cells will start here, some cells will start here, some cells will start here. There is a whole distribution. So, if you think of the initial sizes, there is some whole distribution of this initial sizes P of S naught of this daughter cells when they first divide. Okay. Irrespective of what size it starts out from, whenever they cross this threshold theta, that is when they will divide. That is one hypothesis, that there is some absolute size of the cell roughly, whenever, irrespective of where you start out from, if you hit that threshold, you divide. That would be this first hypothesis. The second hypothesis is that you have to grow by some absolute amount and then you divide, which means that the threshold is not a fixed theta, but it changes depending on what is your S naught. So, it is the threshold is S naught plus some fixed theta. So, that is the second hypothesis. Is that what you were asking? No? You can ask one if it is not clear. You know S naught, okay, you know S naught, fine. Initial area. Right. So, you will have some distribution of S naught for different cells, yes. S naught plus theta, the cell will divide, correct. That is again, that is some parameter, but it is the same parameter for all of these cells irrespective of what value of S naught they started out from. Something would have started out from S naught, something would have started out from S naught prime. You grow by a fixed amount theta and then you divide. That is again a hypothesis. But under this hypothesis, again you can work out what would be the distribution of cell division times, for example. And again you can go back and check in principle. The third is that is this ratio thresholding, where you say that again you have a distribution. If you have a distribution, different cells starting out from different S naught prime and so on, you have to grow to some ratio, let us say R times S naught, and then you divide. The second cell would have to go to some R times S naught prime and then divide. So, it is not a fixed difference, but the ratio of the final size SF by the initial size, this is fixed R. So, this is what is called as the ratio thresholding. So, you grow by a certain factor and then you divide. And again, these are all hypothetical mechanisms. So, but one can work out the consequences of each of these in as much as what does it say about the distribution of times that you have for cell division, and then go back and try to see if you can match the experimental data to these mechanisms. So, that is the idea. Is it clear? So, three things that we need is then of course, this initial size distribution. So, what is this initial size distribution? How does the cell grow, and what is the mechanism of thresholding, that when the cell will divide. Once you know these things, you can formulate that problem in a stochastic sense and try to work out what does it mean for the times. Now, one of the good things about this process is that in general, of course, when you have a stochastic process, so let us say I have some general stochastic process as a function of time xi, right. You will have, like we discussed, you will have trajectories, let us say something like this, and in principle you are thinking about when does it cross a certain certain specified value xi f, which is where I will put, which is where I want to calculate my first passage time from, time 2. In general, trajectories will cross this many times, right, and you only want this first time, right, where it crosses, and that is why we formulated it as an auxiliary problem, where we put an absorbing boundary condition over here, so that up till this point our analysis is good. After that, it is the auxiliary problem and the original problem start to differ. In this case, at least for the cell size problem, because sizes grow monotonically with time. So, if you see these experimental plots, for example, they always grow monotonically with time, which means that it is a little simpler in some sense, in that you always have trajectories which are like this. You always have trajectories which are like this, right. So, they are monotonic. You do not have anything, once it crosses, it does not come back and cross again in that sense. Okay. So, this is, so cell sizes grow monotonically with time. So, in that sense, it is a little simpler problem as compared to the general sort of first passage problems, where you can of course have any sort of trajectories. Here you have a restricted subclass of trajectories that are applicable for this problem. Okay. And what that means is that if I am looking for the first passage, if I am looking for the first passage distributions, f of tau, this was like the negative derivative of the survival up to, let me put a theta somewhere as well, because I want to talk in terms of some threshold theta. This was some, in general, some threshold S of tau theta, derivative of the survival, and in this case it is essentially nothing but the derivative of the probability how do I write this? So, the probability that you have a size, some size s at some time tau, integrated over all sizes from theta to infinity. How do I think about this? So, what I have is trajectories like this, right. So, these are all monotonic trajectories, right, and I am looking at some threshold, I am looking at the time when you cross some threshold value theta, right, within some time, let us say tau and tau plus d tau. that would give me my f tau d tau, right? What is the distribution? So, let me draw a few more trajectories that cross in this time, and then there are trajectories which cross later and trajectories which cross earlier. So, all of these trajectories, or rather the survival, then the survival S tau is all of these trajectories 1 minus all of these trajectories S comma tau d theta integral ds from theta to infinity. So, whichever cells are higher than this threshold size theta, right, 1 minus that is the survival, and then in that case if I put it over here, then the derivative of the survival gives me the first passage. Okay. So, in this case, when you have a monotonic increase of this area, the first passage distribution is a simple derivative of this integral of the cumulative probability from the threshold size theta up to all possible sizes infinity. All right. So, that is what we will try to work out then. So, first we will work it out for the simplest case, which is linear growth, or at least I won't work it out explicitly, but at least we will see how to work it out schematically. So, the linear growth is like this, that you have some size s, right, and you go to some size, let us say s plus 1 with some rate k. Okay. So, what that means is that if I were to write down the master equation, the forward master equation for these probabilities of having a size s at some time t, then the derivative of this probability del p del t would be what? So, these are just growth, right? There is no sort of decay in sizes, which means that you will have a gain term which will come from s minus 1 and a loss term which is will go from s to s plus 1, right. So, the gain term will be k times p s minus 1 comma t minus a loss term which is k times p of s comma t. And is this clear? So, this is the standard equation. So, you have with some rate k, you sort of grow in size by some unit 1, or you could say ds, whatever, it does not matter. And then what you need to solve this is of course some initial condition. So, if you choose the simplest initial condition that you have everything starts off with the same size. So, this says that I guess this is even simpler. I see. So, this is even simpler. So, you say that at t equal to 0, all cells start with an area. So, start with area S naught, which is equal to 0. Okay. This is a sort of extremely simplified case, somewhat unrealistic, because you will never have cells starting with S naught 0, but we will change that in a second. What would be the P of ST for this case? Anyone? What sort of a process is this? It's an unidirectional walk, of course, but the statistics of, so you have a single rate parameter k, which means your times that you wait to for this sort of a process to happen is exponentially distributed, right, with a time scale which is 1 by k. So, what sort of a process is this? It's a Poisson process, right, which means that if you were to solve this, and you should try and solve this, if you were to solve this, what you would get for P of st, sorry, P of s comma t would be what? Would be kt to the power of s, would be kt to the power of s e to the power of minus kt by s factorial. You have a rate k, and therefore the mean size will grow as with time as kt essentially, and you can show that the variance will also grow as kt, which essentially tells you that the distribution is Poissonian with that parameter as lambda parameter as kt, and then that is what you would get for your p of s. Once you have this, of course, you can calculate what is the distribution of first passage times by taking the derivative of this integral. Okay. So, you just take you have this p of s comma t, you take an integral p s comma t ds from theta to infinity, and then you take the derivative of this. Let me write it as tau. Take the derivative of this, and that would give you your f of t, f of tau, for a given value of theta. Again, so if you were to do this, what you would get is a gamma distribution. So, I will just write that down. So, what you get in this case is something like a gamma distribution. It depends, of course, on the thresholding that you put. So, here what we have put a absolute thresholding, that whenever you cross a value theta, that is when you divide, and therefore, we are calculating the distribution of first passage times for these cell sizes to cross this value theta, assuming that all cells started with size 0 at time t equal to 0. So, this is theta is a parameter, and of course, this growth rate k is a parameter. So, f of tau given these two parameters theta and k, and that is this gamma distribution. So, this is k e to the power of minus k tau to the power of minus 1 plus theta divided by gamma of theta. Okay, so is this part clear? This why the derivative is the first passage time? What? Which one? This equation? This is the first passage probability distribution of first passage times, given that you have some size, absolute size theta when the cell divides, and this theta is a parameter. So, what are you now, which part are you now asking? This relation itself or this relation? This relation? Let me just think of it in a slightly different way. So, p s comma tau ds from theta to infinity is the cumulative probability of all cells which have size greater than theta at time tau. Okay. So, 1 minus this therefore is the cumulative probability of all cells which have size less than theta. One second. So, let me just think about this once more. So, this is p s tau ds. So, these are all cells which have not attained size theta within time tau, right. So, therefore, this is my survival probability of up till time tau of all cells which have not reached size theta, correct, because these are all cells which have not reached size theta, right. And then the first passage is nothing but the derivative, the negative derivative of the survival. This you remember from when we are doing. So, the first passage is nothing but f of tau is nothing but the negative derivative of the survival probability, which means this is nothing but the positive derivative of this quantity. So, f of tau therefore is nothing but this derivative del tau. Yes. But in this case, essentially the way we have defined it, the original problem actually has the observing condition, in that once you reach theta, you divide. So, that original cell essentially goes away. So, which is what I meant, that there are no trajectories which, well, essentially there are no trajectories like this. I mean, whenever you reach, yes. Right, actually that is true. Correct. So these are monotonically increasing sizes. So here there is probably I should put a auxiliary condition. Yeah, that is true actually. So when I'm writing this master equation, I have not. This is pure growth. This has no division actually. So there is no absorbing condition at theta. Right. So these are actually trajectories like this, and then I will put the condition that if it crosses theta, it were to divide. So that, and then calculate the first passage time corresponding to that. So there is an absorbing boundary condition on top of this at theta. So this is one set of first passage times. This is one set of first passage times. In this simplest case, where I have started with t equal to 0. Now, what you can do is that you can show that if you were to start with some non-zero value of S naught, everything is still starts with S naught. All cells start with S naught, but now this S naught is no longer equal to 0, and in that case, you just get a shifted Poisson, which means that what you will get is you will get a KT minus S KT. This is KT, this is S minus S naught, and then again you will get some S minus S naught factorial for S greater than S naught. So it's the same Poisson, except it's just shifted. Wherever it was S, you will have a S minus S naught, where S naught is your starting size. And you will get a corresponding FPT distribution corresponding to that. If you now have some distribution, then of course you have to. If you now have a distribution of initial sizes, let us say R of S naught. Right. Then for each value of S naught, you will have something like this, which means that. And so this is okay. So this is the second problem. So this is one problem. Then the second one is actually differential size thresholding. So let us say that you start with S naught, and then you will divide when you reach some S naught plus theta. This is not some absolute theta, but some additive threshold S naught plus theta. And you can have some distribution of initial sizes R of S naught. And given an S naught, you can solve this problem as well. So to get the f of tau as some k e to the power of minus k tau to the power of S minus S naught, right. So generally what you have here over here is S minus S naught in this solution. So in this case, when you have a additive threshold, what you will have over here is simply a theta, right, and then you will have something like a theta factorial. Sorry, this is P. Sorry, this is P of theta comma tau. Okay. And then you can get the corresponding f of t. You can get the this is P of t. You can get the corresponding f of theta comma tau, which is nothing but k e to the power of minus k tau to the power of minus 1 plus 1 plus theta, and by gamma of theta. Remember, this theta is actually the difference between the initial size and the final threshold size. And if you have some distribution, then you have, of course, have to convolute this with the distribution of initial sizes R of S naught for all values of S naught from 0 to infinity. So this we did for this fixed S naught, right? For what you have for fixed S naught, is you have a S minus S naught that appears over here. So, if you have this additive thresholding, this differential size thresholding, then what comes over here is this difference, which is what I have called as theta over here. And then everything comes in terms of this theta, this initial size S naught goes away, right. Now, if you have some distribution of sizes R of S naught in the beginning, right, then you would of course have to take this average, that f of theta would be weighted by this distribution R of S naught, correct. But this R of S naught, there is no other S naught appearing anywhere else, right, in this equation. And of course, integral R of S naught or summation R of S naught for all values of S naught must be 1, which means that this summation is trivially 1, and you will just get whatever you have over here, which is k e to the power of minus k tau, sorry, k tau to the power of minus 1 plus theta by gamma of theta. So, if you have something like this, then this initial size distribution drops out of the final equation. All that matters is what is the size of the differential threshold. It does not matter what is the distribution of initial sizes R of S naught. Again, this is assuming linear growth. If you did not have linear growth, you would have different results, of course. So, I start off with an initial for a particular cell. I start off with some initial size S naught, right, and I say that it will divide when it reaches a size S final equal to S naught plus theta, right. So, if I were to solve this process using this master equation, right, what appears over here in this Poisson distribution is the difference between the final size and the initial size, which is a constant theta, right. So, therefore, the formula that I have over here is k tau to the power of theta by theta factorial, which is independent of what initial size you had started out, what initial size S naught you had started out from. Okay. So, that is for some particular cell which started off with S naught. Now, if you want to know the full f of tau, you have to average over the full distribution of initial sizes, but because the distribution of initial sizes is normalized, and because this has no dependence on the initial size, you will get that this f of tau is also independent of the initial size distribution. It just depends on your differential threshold theta, which is what is the amount that you are adding to this initial size before you have to divide. The next thing that one can try out is exponential growth. And again, this is something that you have done. So, if you have exponential growth, so that was linear growth. If you have exponential growth, what sort of how would I modify this master equation to get exponential growth? Anyone? Yes. So, del Ps del T is k s minus 1 p s minus 1 comma t minus k s p of s comma t, right. So, remember these birth processes where we I think quiz 1, right, where we did these rates being dependent on the size itself. So, this is a process like that. And this you had solved technically in the quiz, or at least it's there in the model solution. So, this one can write. So, if you have a process like this, you can write down what is the full solution of this S, P of S comma T or tau, given some initial condition S naught and some rate over here K. So, this, if you remember, was S minus 1, S naught minus 1 minus k tau to the power of S minus S naught e to the power of minus k tau S naught, and this is for S greater than S naught. This is for S greater than S naught. So this is something. So again, so writing down the master equation is of course easy. Solving it is not trivial. So I'm not working out this solution. This is exactly the quiz solution that we had done. So you will get some A like this, some probability distribution like this. So this is the negative binomial. So this is the negative binomial distribution. If you want the first passage distribution, so if you choose an absolute threshold, if you choose some absolute threshold, again, if you choose some absolute threshold theta, if you choose some absolute threshold theta, you can work out the first passage distribution given for a given choice of this absolute threshold and for a given choice of this rate parameter k. And this would be some k e to the power of minus S naught k tau 1 minus e to the power of minus k tau to the power of minus 1 plus theta minus S naught I the beta function S naught. So again, I'm not doing the intermediate steps, but this one and the papers it refers to has the full detailed calculations, which you should try and work out. If I were to choose a differential threshold, so if I were to choose instead of an absolute threshold, if I were to choose a differential threshold, which means that I divide when I reach SF, which is S naught plus some constant theta. Here, of course, this the final size would become S instead of theta, it would become S naught plus theta. So here you would not get any dependence on the initial size, but this term would continue to have a dependence on the initial size because this is a e to the power of minus S naught k tau. So this would not get the S naught would not get out of this if you were to do a differential threshold. So, for example, if you were, therefore, what it says is that if there is a differential threshold, and so therefore, in this case, if you were to find out what is f of tau, it would have some dependence on what is the distribution of initial sizes that you have. Correspondingly, on the other hand, if we had linear growth, there would be no dependence on what would be the distribution of initial sizes. So, each of these hypothetical possibilities has implications on what you would see for this distribution of cell division times, depending on what sort of growth process it is and what sort of thresholding approximation you use. So, therefore, given a data, one can sort of try and test out that which of these hypotheses makes sense for your particular data, right? And therefore, what is the underlying mechanism at play? So, here, of course, for the differential size threshold, it depends on R S naught. For the absolute, for example, if I were to choose the ratio threshold as well, this theta would become R S naught. This would also become R S naught. And here also I would have an S naught. So that would also depend on the distribution of initial sizes. So both of these in this, for this exponential growth, for both of this, you have a dependence on initial size distributions. Dependence on initial size distributions. So that's a sort of basic, and so this is one sort of process. So we talked about cell birth processes. There are various processes which you can think about in a similar fashion. For example, protein copy numbers. If you have proteins which are being produced and being degraded, you could imagine that certain biological processes happen when the copy number of a particular protein crosses some threshold number. Okay, and again that would be described by something of a formalism of this sort. Cell growth is of course described by a formalism of this sort. You can map different biological processes to somewhat of a similar backbone architecture and then work out the distribution of times for those particular biological processes. in this case cell division, but like I said, there are the similar sort of framework has been used in different contexts, lysis and then endocytosis and so on and so forth. So, I will stop here for this, at least for this cell division process, and just talk a little about resetting processes, which is one of the assignment problems. So, this I sort of did a little bit of hand waving, but you should go back to the original paper and try to work out the full mathematics and hopefully convince yourself that whatever we have, whatever is done is sort of correct. Okay. These are a couple of this one, but review, but also the papers that is cited in the review has the full detailed calculations. So, one more thing, which is then this resetting process. So, just for the resetting process, I will just write down the backward equation and then the solution you can do anyway as part of the assignment. This is, for example, a distribution of cell division times actually from actual experiments, and you could try and fit this sort of data. I think this is from the Caulobacter crescentis experiment, which has exponential growth, and you can then try to fit this sort of distributions given these free parameters that you have theta and k, and try to see what sort of thresholding process makes sense for a given given cell type. But in general, these distributions of cell division times are unimodal and also fat-tailed, which is a property of these distributions that we derived. All right. So, the second problem is resetting. And again, this is a class of problems which has been came up from stochastic processes, but has been used in different biological contexts, in particular search processes and foraging and so on. So, what this says is that let us say you are doing a random walk and you want to find some target. So, let us say you are starting out your random walk from some initial position x naught, and you have to find a target somewhere, right. So, you do a random walk and so on and so forth. Maybe you one walk finds the target, but then of course, because let's say there is a 2D random walk, there will be random walks which will go completely in the opposite direction, and then it would have to come back all the way to find the target. So, if you are thinking about search strategies, sometimes it might be optimal to reset your search process, which means that you walk for some time in whatever direction that you choose. If you find the target, well and good. If you do not find the target, you reset yourself back to the origin, whatever is your origin position x naught. Okay. So, that is called resetting. So, for example, in a biological context, for example, you could think of when a cell is dividing, you have these chromosomes, you have the spindle poles, structure, and here are your chromosomes, right. Spindle poles are made up of microtubules which polymerize and depolymerize, and if a microtubule latches on to this chromosomes, then it attaches itself to them and drags it down. So, that is how the two copies of the chromosomes get separated out, okay, when the cell is dividing. You could think that if microtubule is growing in some wrong direction, it could go past these chromosomes, and therefore it would waste a lot of time sort of searching in an area where the chromosomes are not there. In such a case, it might be beneficial to sort of reset your search process. So, microtubules always go from the spindle pole. So, you have a polymerizing microtubule. After some time, if it does not find the target, it depolymerizes very quickly and again starts polymerizing in a different direction. So, that would be an example of something like this, a stochastic reset. So, the process is that you do some random walk. If you find the target, good. If you do not find the target, or rather you sort of, as you do the random walk, you reset yourself to the initial position with some constant rate in the simplest version, and then you start the process again. So, is this clear? So it resets with a rate. So there are various formulations. The canonical formulation is that you reset with a constant rate r, which means typically after a time 1 over r you will reset, but it's a stochastic process. So in some cases you might reset very fast, in some cases you will reset, but you have some constant rate r of resetting. So I think the assignment problem that I had given was a simple, this simple one-dimensional diffusion. This is simple one-dimensional diffusion. So I have an absorbing boundary at x equal to 0. Okay. At x equal to 0, I start a particle at some position x naught. Or let us say I start a particle at some position x. It does a random walk. Sometimes it walks here, sometimes it walks there. And the probability of hops, so it's a symmetric random walk. So it's a symmetric random walk. Symmetric random walk with hopping probability, with a hopping rate of p, and a resetting rate of r, and a resetting rate. So when it resets to this position x naught, and then again starts doing resetting rate. Okay. And then I think I had asked to write down the backward equation for the survival probabilities, right? Is the setup clear? So if I'm writing the backward equation, so I'm writing it for the survival probability S, okay, S of tau, starting from some position x. So I want to write down the backward equation. Okay. So what do we do? So again, remember there are two sort of terms. So you have, in the first case, so I sum over all intermediate states x prime, right, of going from x to x prime with some rate, and then you have the survival probability from x prime. That is one sort of a, and then you have the same rate tau comma x omega of x prime comma x. So this is the structure of the backward equation. The same rate appears in both terms, in the positive term as well as the negative term, which is the rate of going from this initial position x to a different position x prime, right? And in this case, this is then from going from x prime to whatever is your final absorbing state. This is from x to your final. So this came from the term that you did not escape in that initial time delta t, and this came from the term that you did escape in that initial time delta t. So in this case, when you have this random walk, but with this additional term, additional reset term, what are the possibilities? So you start from some x. Where could one have gone in the next instant of time? X plus 1, and okay, and these rates are p, right? So you could have gone to p s of x plus 1, and then minus. So what is the resetting term? R times S of x naught, right? Because you could have gone to the resetting position x naught with a rate r, and what would you have here? You would have S of tau comma x, right, times the same rates. So p plus r, right, because it's the same rates omega x prime x that appears over here. Because that is the, because you start off from x, you can hop here, you can hop there, or you can go there. Rate of resetting is r. So that from any position, these are the three options that you have. And so this would be your resetting, this would be your backward master equation. And this, of course, these terms p, this p, and then this 2p, these are my standard diffusion terms. So this would just give you a d if you were to do the Taylor series expansion and so on. This would simply give you a del 2s del xs square and plus whatever is left. So r of s tau comma x naught minus r of s tau comma x. So the standard diffusion term, but also these two additional terms, one from here and one from here, which correspond to your resetting, which correspond to the resetting terms. And then once you have written down the backward equation, of course, it's a question of solving it so that you can try and solve. But essentially what one shows, or at least what you should be able to show, is that if you look at the time taken to find the target in this case is x equal to 0. Here is where I put the absorbing boundary condition. So x equal to 0 is absorbing. So how long does it take to reach this origin? You can plot this time or rather the mean time taken, let us say, to refine this target starting from x naught as a function of this resetting rate. And there what people showed is that you have some non-monotonicity, which means that there is some optimal reset rate where the search process is most efficient. So if you reset very slowly, so essentially you have this search process, you're going and finding your target, and you will have trajectories which will take you away from the target. So if you reset very slowly, if your resetting rate is very small, these trajectories can go away. You will waste a lot of time in these trajectories and not finding the target. On the other hand, if your resetting rate is very large, then even before you reach the target, even if you were going in the right direction, you will get reset to the origin, right? So therefore, there is some optimum resetting rate r star, where you will get some minima in your search time. So there is some optimal strategy for how often one should reset in order to find your targets fastest. And again, this is something that you can find out what is this r star if you solve this equation analytically. So I just wanted to write down the backward equation, and then the rest you can do. Okay, so I'll stop here. I think we have done a fair amount of backward equations, and then there are a fair amount in the assignment as well. So if you solve all of these, hopefully you'll get a handle on how to write down backward equations, and from there how to calculate these sort of times of processes.